solving thermodynamic problems involving water, we rely on state properties to calculate changes. Let us see how we can use water property charts to acquire state properties. First, let us get familiar with the temperature entropy chart for water. With this, we plot the constant pressure lines, isobars, the constant specific volume lines, isocores, and finally, the constant enthalpy lines. We understand that we can use these charts to acquire state properties, say within the saturated or the superheated region. Of course, we need more detailed chart to solve common thermodynamic problems in the textbook. So let us build one. A detailed TS property chart has numerous constant property lines that we can use to retrieve thermodynamic properties of water. We begin with our axes. Entropy S is on the x-axis and temperature T in Celsius is on the y-axis. We first plot the isobars in megapascals. Because the phase change process happens at a constant temperature, we can eliminate these isobars within the dome, just to reduce clutter. Instead, let us bound this area with a saturated liquid line to the left and a saturated vapor line to the right. In between, we can populate the mixture dome with constant quality lines going from 0% to 100% vapor. Densities are only plotted in the superheated region and not in the saturated region to avoid confusion. Also, notice that these do not increase arithmetically. They are multiples of 3 and 3 1/3. More on this later. Finally, we add the constant enthalpy lines to complete our TS property chart. The TS property chart can be divided into multiple regions. First, we have our compressed liquid region. Here, the pressure does not have much of an effect on the properties. Then we have the saturated region, where we have a mixture of liquid and vapor phase water defined by quality X. The supercritical region is above the critical temperature of 374 degrees Celsius and a pressure of about 22 megapascals for water. And finally, we have the superheated region to the right, where water begins to behave like an ideal gas. Let us practice retrieving properties from these different regions. For this, we're going to pick a constant pressure of 2 atmospheres. That's about 200 kilopascals. We begin at 500 degrees Celsius. This state is in the superheated region. Collect the easiest properties first. The enthalpy value on the green line and the entropy on the x-axis is a good starting point. The specific volume requires an extra step because the sequence of density line is geometric rather than arithmetic sequence with a common difference. First, we understand that specific volume is the inverse of density. Next, we must identify the 2 lines that bound our state and calculate the ratio, 3 1/3 in this case. Then, the density of our state is the lower density times the ratio of the 2 densities raised to the power that is the fractional distance from the lower reference to our state. Here, our state is about halfway between, and hence we raise it to the power of half. This gives us a density of 0.55 kilograms per meter cubed, which when inverted gives us the specific volume of 1.8 meter cubed per kilogram. Internal energy is not plotted on the TS chart, but we know that the internal energy U is a function of enthalpy, pressure, and specific volume. So we plug those values in and arrive at our internal energy of the state. At this point, we have retrieved all the properties required for the superheated state. Next, let us use water at 200 kilopascals but cool the water to partially condense it to get a mixture quality of 60%. Again, there are state properties that are easy to read off. The saturation temperature is 120 degrees Celsius, the enthalpy, and the entropy. The specific volume within the saturated region is bounded by the saturated liquid value to the left and the saturated vapor value to the right. At the saturated liquid line, the specific volume is 0.001 meter cubed per kilogram. That's the inverse of 1,000 kilograms per meter cubed for liquid water, and you know this. The value to the right needs to be computed just like before. That state is bounded by 2 constant density lines with a ratio of 3. Here, our state is about 1/10 of the way to the next line. Using a similar approach as before, we get the vapor phase specific volume. However, our state is only 60% vapor. For this, we're not going to worry about the liquid phase and simply take 60% of that vapor phase value. Internal energy is straightforward now because you have all the needed values. So plug these in and get your internal energy. We are done retrieving all the properties for our mixture state. We're going to keep cooling this mixture. at 200 kilopascals until we have liquid water at a temperature of 50 degrees Celsius. Liquids are considered incompressible because they do not change their properties much with pressure. Therefore, we can safely assume that the properties of a liquid can be estimated using the saturated liquid properties at the same temperature. So we move over to the right and read off our state properties on the saturated liquid line at 50 degrees Celsius. The specific volume is simply 0.001 meter cubed per kilogram. And because of the small specific volume, the internal energy and the enthalpy are nominally the same. Again, we have all the properties for this liquid state. This way, property charts are very useful for quickly retrieving property values. Additionally, they provide a realistic depiction of a steam power cycle. A power cycle is used to generate electricity, and the simplest one is composed of 4 states. We first pump liquid water from state 1 to 2. This is only a minor change in location on the chart. Next, we use a boiler to heat the liquid water to a superheated state. This superheated state is then fed into a turbine where we extract the energy to drive the electrical generator. Finally, we use a condenser to bring the state back to where it started. We can now use this cycle to predict the performance of our power station. Now I understand that this is a very simple cycle, but you can already see the benefits of using property charts.